Swayam Prabha. Digital India. Educated India.
The very first question I am going to ask in this is, if I take a rigid body and rotate it with respect to axis x, axis y and axis z, can I take its rotational angle theta as a vector? I would give the rotation about x a direction along x axis, rotation about y a direction about y axis, and rotation about z a direction about the z axis. The question is, do these quantities together, if I take this plus theta y j plus theta z k, does it constitute a vector quantity? And the answer to this in one word is no. No. Theta, if I take this to be as theta x I plus theta y j plus theta z k, is not a vector quantity. And reason for this is very simple, as I will now illustrate. Let us take a small rod thin of length L along the y axis, so that its this end has coordinates 0, L and 0. I will now do two operations on it. I will first rotate it about the x axis and then about the z axis in counterclockwise sense, and then do it the other way. I will first rotate it about the z axis and then about the x axis. If theta is a vector, then theta, if this is given as theta x I about the x axis plus theta z k, it should not really matter whether I do it this way or do rotation about the z axis first and then about the x axis. Let us see if this comes out to be the same. So, let this be the thin rod, let this be the y axis, let the x axis be coming towards me, x, y, and this is the z axis, x axis, y axis and z axis. Let me first give it a rotation counterclockwise sense about the x axis. So, x axis is coming this way, counterclockwise sense would be like this, and let me now rotate it by 90 degrees about the z axis. So, this is how it looks. Let us now do the same thing first about the z axis and then about the x axis. So, this is the z axis, let me rotate it by 90 degrees about the z axis, then it rotates like this, and about the x axis, if I rotate counterclockwise by 90 degrees, it rotates like this. So, you see in the two operations, if I carry out the rotation about x axis first and then about the z axis, the rod ends up rotating in this final position. On the other hand, if I give rotation about the x axis first, about the z axis first and then about the x axis, it ends up coming in this position. That means the two theta x I plus theta z k is not the same as theta z k plus theta x I. Let me show it again. So, what I did was took the x axis, y axis and z axis, took the rod along the y axis. So, that its coordinate was 0, L and 0. Then I first gave it a rotation of 90 degrees about the x axis in counterclockwise sense, and then rotated it about the z axis again by 90 degrees. This was not the same as rotating it first about the z axis and then rotating it about the x axis. Let us see it mathematically. If I rotate this rod about the x axis counterclockwise, the new coordinates of this would be x prime would remain 0, y prime would become 0 and z prime would become L after the first rotation. After the second rotation about the z axis, nothing really changes, only it has just rotated a bit. On the other hand, let us see what happens if I rotate it about the z axis first and then about the y axis. So, let us write this x, y, z. This was the rod at coordinate 0, L and 0. If I did 90 degrees about the x axis plus 90 degrees about the z axis, the coordinates after this rotation came out to be 0, 0 and L. So, rod was in this position. Let us now do first 90 degrees about the z axis and then 90 degrees about the x axis. When I rotate it 90 degrees about the z axis counterclockwise, it will go this way, so that its end would have coordinate x prime is equal to minus L, y prime is equal to 0 and z prime equal to 0. After that rotation, if I rotate it by about the x axis, nothing really changes. So, the coordinates of the end are x prime, y prime, z prime equals minus L, 0 and 0. You can see that the two sets of coordinates do not match at all. What that means is that the two rotations, I can't really represent this as a vector, it has no meaning, because it changes according to how I apply these rotations, in what order I apply these rotations. So, angle theta cannot really be a vector, but there is a saving grace. Saving grace is that although angle theta, a finite angle theta, is not a vector, any infinitesimal change delta theta is a vector quantity. How? Let us see that. Again we go back to our rod. This is my x axis, this is y axis, this is z axis. So, what I am going to do is apply a very small rotation delta theta x about the x axis. So, the rod is rotated like this. After this rotation, what about its new coordinates of this end? To start with, this was 0, L and 0. You will see that x prime remains 0. This angle is delta theta x. You can see y prime is equal to L cosine of delta theta x, which for very small delta theta x is really L, and z prime is equal to L sine of delta theta x, which for very small delta theta x is L delta theta x. So, the new coordinates after the first rotation for the end of the rod that I get are x prime y prime z prime equals 0 L and L delta theta x. This is after I gave it the first rotation about the x axis, x, y and z. Now, let me rotate this rod about the z axis by an angle delta theta z. When that happens, you can see that x double prime, which is after the second rotation, is going to come from this projection going back by angle delta theta z. So, this is going to be minus L sine of delta theta z, which is roughly equal to minus L delta theta z. Y double prime again is not going to change. So, this will remain L cosine of delta theta z, which is roughly equal to L, and z prime is also not going to change because now it is a rotation about z axis. So, this is going to remain L delta theta x. So, the new coordinates that we get after the two rotations have been done, that is a small rotation about the x axis by amount delta theta x and followed by a small rotation about the z axis by delta theta z, gives you the new coordinates starting from 0 L 0 coordinate. Rod starting from this position is minus L delta theta z, L and L delta theta x. This is going in the order when I rotate it first about the x axis and then about the z axis. Let us see if I change the order what happens. So, now what I am going to do is take the same rod, x axis, y axis, z axis, first give it a rotation about the z axis in the xy plane by an angle delta theta x counterclockwise. So, when it rotates like this in the xy plane, you can see that x prime, this will be like this in the xy plane, is going to be this projection. This is delta theta z, is going to be minus L sine delta theta z, which is roughly equal to minus L delta theta z. Y prime is going to be L cosine of delta theta z, which is roughly equal to L. Since this is a rotation about z axis, z prime remains unchanged. So, after the first rotation about the z axis, I have x prime, y prime and z prime is equal to minus L delta theta z, L comma 0. Now, let me give it a rotation about the x axis. So, now I am starting with the rod in xy plane like this and give it a rotation about the x axis by amount delta theta x. Since I am giving a rotation about the x axis, the x coordinate cannot change. So, x double prime remains as it was earlier, minus L delta theta z. Y double prime would remain L cosine of delta theta x, which is roughly equal to L, and z prime, now it is moving up, the L length is moving up and therefore, is going to be equal to L sine of delta theta x, because now this will be moving up like this in the y z plane and this will be equal to roughly L delta theta x. So, after these three rotations, I end up getting x double prime, y double prime, z double prime is equal to minus L delta theta z comma L delta theta x, which is precisely the same which I got when I had the other order, first rotation about the x axis and then rotation about the z axis. Let us see that is in the previous slides somewhere. Here it is. This was earlier and here it is now. This is now. So, earlier minus L delta theta z, L delta theta x, and now minus L delta theta z, L and L delta theta x. So, when I take infinitesimal rotations, when the second order product delta theta x delta theta z vanishes, what I get is that delta theta I can write as delta theta x about the x axis plus delta theta z about the z axis. Does not matter which order I apply in, I get still the same answer. I get x double prime, y double prime, z double prime as equal to minus L delta theta z, L and L delta theta x, which I can write as the original L j plus delta theta x I plus delta theta z k cross the original vector, which is L j. This would be by the definition L j plus I cross j is k delta theta x times L k plus k cross j is minus I. So, minus delta theta z L I, which is precisely the same as this. So, what we understand is that when I apply very small rotations, the rotations commute and I can represent them as vectors. Although I took here the example of delta theta x and delta theta z, which are rotations about x and z axis, I could have chosen any other combinations and shown that even if I apply a third small rotation about the y axis, they will all commute. So, what we get from this is that I can write the new vector r, which I obtain if I had a vector somewhere. Let me generalize the result, and I rotated it by a small angle delta theta, which I will write as a vector, which could be delta theta x about the x axis, delta theta y about the y axis plus delta theta z about the z axis. Then I could write r prime as equal to the original vector r, this is the original vector, and this is r prime plus the change in r, which will be written as delta theta cross r. Having shown this, let me now show it in a slightly different way. Let us take an axis of rotation in direction n, unit vector direction n. Let there be a vector r, although I am writing it for r, r could be any general vector, and let this vector r rotate about this axis like this, so that after an infinitesimal rotation about this axis, this new position is here. It has rotated by an angle delta theta about the axis n. How much is this change? For very small angles, this change can be written as, this length is going to be r cross n magnitude, because this is going to be, this length is nothing but this sine of this angle, which is nothing but r cross n magnitude. This direction is perpendicular to this, and you can see that this is actually n cross r direction. So, what we see, if I make the circle here, this magnitude is n cross r magnitude, and it has changed by this amount in the direction of n cross r by an amount n cross r sine of delta theta, which is roughly equal to n cross r delta theta, and this is your delta r, because this is how much it has changed. Let me make the figure again. I have taken an axis in the direction of unit vector n, taken a vector r which is rotated by a small angle delta theta, and I want to know this change. This direction is automatically n cross r, and this change delta r is n cross r, right direction, right magnitude of this radius times delta theta, and therefore, taking the direction of delta theta along the axis of rotation, I can write this as delta theta cross r, and therefore, the new r prime is really the original vector plus delta theta cross r. What I have shown you is, in the previous derivation where I wrote delta theta as this and then derived delta r, and after that wrote r prime equals r plus delta theta r. Now I have taken a general axis of rotation n and shown again that r prime can be written like this. Therefore, this is the general result, that if a vector rotates about an axis in unit vector direction n by a very small angle delta theta, I can write the change as this cross product. This is an absolutely general result. Although I have written here taking r as a vector, this could in general be any vector a. The change would still be this. So, this is the first general result we get, that for a rotation about an axis pointing in direction n, a small angle delta theta rotation gives rise to change delta r is equal to delta theta cross r.